So good morning. My name is Kevin Retzke. I'm in the Scientific Computing Division at FermiLab. Now, I myself am not a scientist. My organization's role is to provide the computing resources, tools, and other support that the scientists need to fulfill their mission. My group itself is mainly focused on distributed computing, and I, of course, do monitoring. That's why I'm here. So today I'm going to talk a little bit about FermiLab and how we're using Grafana to monitor our scientific computing services. So first, a disclaimer. All opinions and views I give are my own, are not to be construed to represent those of the US government or any of its agencies. I'm not endorsing any products on behalf of the US government here. A little bit about FermiLab. Fermi National Accelerator Laboratory, founded 50 years ago. We're actually be celebrating that anniversary up here in a couple weeks. We're 40 miles west of Chicago. At the time when we started, it was pretty much out in the middle of nowhere. Suburban sprawl has really grown up. But FermiLab itself, still really a very green place. I'll talk a little bit more about why that is. And FermiLab is really dedicated to open science for everyone. It's pretty unique among government labs in that way. I mean, really, anyone can come and visit us. We have a lot of outreach programs, visitor centers. There's no secret nuclear research that happens. So all very open. So it's the same way with the science. Thousands of scientists from around the world collaborate on experiments and use FermiLab's facilities. So FermiLab, as the name suggests, is about accelerators. It was built to house the world's largest and most powerful accelerators. For several decades, the Tevatron, that's the big ring in the back right corner there, was the world's highest energy particle accelerator. Shut down about 5 years ago when a larger accelerator was started up at CERN. That's the LHC, you probably heard of that. So at the time, the Tevatron was shut down, and really, because of the limitations in science funding these days, it doesn't make sense to split resources like that. So we've focused effort, at least on the high energy physics side, focused onto the LHC. Then our accelerators refocused into what we call producing higher intensity, that is, more particles on target rather than faster particles. This is especially important in one of the main focus areas of research right now, which are neutrinos, which are these really tiny ghostly particles, very light mass. For a while, I think they weren't even sure they had mass. They do, so they travel not quite at the speed of light, very close to the speed of light. And some interesting things about neutrinos is they also have no charge, which means they really don't want to interact with anything. Which makes them really hard to study because the only way we can study these particles is how they interact with other matter. So highlight we have many neutrino experiments. The flagship right now is NOVA. You can see so it's running off the main injector. That's the big loop in the lower corner, which is our highest energy or our biggest accelerator right now. So there's a near detector on site. That's the one in the upper right corner. It's modestly sized, I suppose. But then we have a far detector several hundred miles away underground in Minnesota. And I don't know if you can see the guy in the little corner there, but it's just a massive detector. It's composed of hundreds of thousands of detector cells. These are on the order of a couple meters long and maybe 10, 20 centimeters in diameter. I'm not exactly sure. But each one of these is filled with a scintillation fluid, and so when a particle has an interaction in there, it emits light, they can detect that light, and that's how they detect neutrinos. NOVA's what they're looking at is the oscillations in fundamental properties of neutrinos. So as the neutrinos move, the properties change, and they're really kind of trying to study what that is and why that is. My understanding is it takes about 3 seconds for a neutrino to get from the new detector to the far detector. So over that time, they can observe how it's changed. And then back on the energy frontier. So the LHC at CERN is really pushing the energy frontier these days. While the accelerator may be in Europe, the US is still a very large contributor to this effort. FermiLab is the US home for the CMS experiment. That's the compact muon solenoid. You can see the detector in the picture there on the right, and apparently that's compact. And that's one of the two main detector experiments on the LHC. FermiLab houses a remote operations center for it, and also provides a large portion of the global computing capacity and support for the computing. FermiLab also looks to the sky. So one of another experiments is the Dark Energy Survey, which has a camera that's built at FermiLab, and my understanding is it's the largest CCD camera in the world at 570 megapixels, so what is that, like 100 iPhones? And it takes high-resolution photos of the sky, and I don't know exactly what they're looking for, but it's something to do with dark energy. They repeatedly scan the sky, look for things that change, and can use this to study dark energy, dark matter. And also a really cool thing they're doing is they're involved in the LIGO experiment, which you may have heard of. They made really big news this past year with the first detection of gravity waves. And so what they really want to be able to do with this is detect gravity waves and then be able to point a telescope, and so they know, okay, it's approximately in this area in the sky. So the telescope, go look and see if there's actually some visible event in there and other particles. We can also, down the road, they'd also like to be able to use our neutrino detectors to detect neutrinos coming from these events and correlate how all these particles correspond to this one event. And last but not least, the FermiLab, at least in the Chicagoland area, is probably best known for our bison herd, which is perhaps unusual for a lab. It's kind of an interesting story behind it. The first director of FermiLab, Robert Wilson, was a bit of a Renaissance man. In addition to a physicist, he was a sculptor and a naturalist. And so his version for FermiLab included not just driving science, but also art and nature. And so the bison herd is part of his vision to bring back and restore the Illinois prairie on the vast land that that FermiLab has. Because a lot of our infrastructure is underground, and just, well, big rings, you have a lot of open area. Now the herd side is maintained. It's not left to just grow free. All they'll tell us is that they send them off site. They won't admit to whether or not they make it back on Bison Burger Day in the cafeteria. Whether or not they are, it's pretty tasty. So there in a nutshell is kind of FermiLab. It's all about science, all about open science, and really it's a scientific leader in the US and the world. And so I have a little video here, hopefully it'll work, to kind of highlight a new experiment that's currently under construction that's similar to NOVA, but it's bigger, better, and it's going to be on a much larger scale.
This is FermiLab, a Department of Energy national laboratory near Chicago. It's the starting place for the Deep Underground Neutrino Experiment, DUNE, powered by the Long Baseline Neutrino Facility, LBNF. The experiment begins with FermiLab's accelerator complex, which moves protons close to the speed of light. It's all part of an effort by more than 1,000 scientists from around the world to figure out how tiny particles called neutrinos work, and what role they play in the evolution of our universe. Neutrinos are the most abundant matter particles in the cosmos, but very hard to catch. Trillions stream through you every second without leaving a trace. At LBNF, the beam of protons will smash into a target, creating the most intense beam of neutrinos in the world. Scientists will collect data to measure properties of neutrinos close to the source and again far away. Neutrinos change as they travel, so scientists are sending them straight through 1,300 kilometers of rock toward the DUNE detectors at the Sanford Underground Research Facility in South Dakota. The detectors can also look for the birth of neutron stars and black holes by catching neutrinos from exploding stars. The 1.5 kilometer deep detectors will be filled with 70,000 tons of liquid argon, making them the largest neutrino detectors in the world. As neutrinos interact with the cold liquid, they create a shower of other particles and light. Those particle tracks are then picked up by electronics and transmitted as data to the surface. The information will be analyzed by scientists at collaborating institutions in countries around the world. They'll use this data to solve unanswered questions about neutrinos, and maybe even figure out why matter exists. Things like planets, stars, and even you.
So there you go, there's the science. And so you saw it's collecting a lot of data, right? So let's talk about the computing. One thing all these experiments really have in common is that they rely heavily on computing. So the Scientific Computing Division at FermiLab meets the needs that they have. There's kind of three broad areas that in the computing that they do. So before they even have a detector or an accelerator, they have to do all kinds of modeling simulation to optimize the design of those accelerators and detectors. So once you have your detector running, then you have to collect and collate the output from these hundreds of thousands, probably maybe even millions, some of the bigger ones, of sensors. And you need to turn all this data streams into something resembling an actual physics event. Physics event being like a cascade of particles, just interactions. And then once you have that, you need to take that data, analyze it to fit it to physics models, either known physics models or develop new physics models like, oh, hey, we don't know what's happening here, and it turns out that's the Higgs boson, which was the big discovery recently. So scientific computing at FermiLab provides that support. I think around a third of the staff at FermiLab is in computing. We have 3 data centers, which altogether provide around 70,000 cores for just doing the computations. That number changes constantly. Plus thousands more of the supporting systems to support these computations. We have about 100 petabytes of active tape storage, and I understand the capacity in our tape robots hits up to about 500 petabytes. In front of the tape, there's about 40 petabytes of disk cache, which is also used as scratch space. This is where the jobs are writing to and reading from. And that's just on site. We also have access to a dedicated high-speed network, which through an organization called the Open Science Grid can connect us to many dozens of sites worldwide. That's other labs and universities. And so we can spread out computation, not just on site, but to other sites, and vice versa. They can come to our site. So within the computing realm, there's kind of 2 distinct, but it's actually, the line's blurring. I think in maybe 10 years, there may not even be a distinction. There's high throughput computing, which is where you run many small jobs with modest resource requirements. They might just need 1 core, a couple gigabytes of RAM, and it may take a couple days up to a couple hours up to a couple days. On the other hand, the high performance computing is where you run one job that uses tons of resources, thousands of nodes, all kinds of memory. So I'll talk more about the high throughput computing because that's the area I'm in. The high performance, my understanding is that we have several clusters. They're smaller, used primarily for test and dev, for workflows. And then when they really need the computing, they send it out to the really massive supercomputers like at our neighbor Argonne or Oak Ridge. So within high throughput computing, we have 2 primary batch systems. One is dedicated for the CMX experiment. Like I said, it's one of the big experiments out of the LHC. And the other one is for, well, everyone else. We have tons of smaller experiments, and small meaning it might be just a couple scientists up to a couple hundred collaborators. And these are all unified under the FIFE project. That's the Fabric for Frontier Experiments. And we provide common tools, infrastructure, and support for all these experiments. So they get resources they otherwise wouldn't really have the funding to get. So to give you kind of an idea, here's kind of a high-level view. I'll try not to go into too much detail on this, of our batch system. So a user submits jobs, or more typically a cluster of thousands of jobs into the batch system. And based on the requirements of that job, the system will go out and provision resources on clusters, either on-site, off-site, anywhere. Really just says, hey, who can provide me with some resources right now to run this job? Once the resources are available, it reports in, so our system will send the job there. And when I'm talking about a job, typically it's just a batch script which set up an environment, and then it'll transfer in any executables and libraries it needs off something of a shared file system, and then it also transfer data out of our data handling systems, and it could be up to a couple gigabytes per job. So the job's going to process that data. Like I said, it could take a few hours. And when done, it's going to transfer the output back to our same batch or data handling systems. Again, this could be a couple gigabytes per job. So that's kind of the overview. Rinse and repeat. Do that about 1 million times a week, at least for FIFE. And CMS is actually a couple, maybe an order of magnitude more than that. So as you can imagine, or as you probably know, complex systems tend to spawn complex monitoring systems. So every service in there, this is a couple of years ago, kind of had its own monitoring, and mostly homegrown stuff. So, okay, we'll pull some numbers out of our SQL database and throw it up on a web page, maybe some PHP, or we've got some RRD files, we'll just throw those up on a web page. So you get this, you have to go all over the place to try to figure out what's going on with the batch system. Like when I first started at FermiLab, I was given a list of links. Okay, if you need to see what's going on, you can follow these links, and somewhere in there you'll identify what's going on. So about 2 years ago, we decided we need to do something to unify this monitoring together, to provide a common system for this monitoring data and a common platform to present this monitoring data to the many users, groups. That's everyone from the scientists, who are the users, to people like me, the service providers, to management, and to stakeholders, people who are invested in the experiment and want to see what's going on. And obviously, since I'm here, Grafana was chosen as our primary user interface. So here's kind of a high-level view of our monitoring system. So on the left, we have all the various systems that we monitor, primarily batch systems. These are all running HD Condor. So we have maybe a half dozen of those that we're monitoring right now. Then all the various data handling systems. Some of these are more industry standard, at least in high energy physics. Some of these are homegrown. Some of the homegrown systems actually report stats directly to our databases. And so we have probes running, and most of these services provide some sort of API, at least, that we can query. So we have probes, which are mostly Python. We'll run about every 5 minutes and pull down metrics from these systems. And they actually send out 2 data streams. We'll send time series aggregations to statistics into our Graphite database. Then we also put raw documents and various log files, which go into Elasticsearch. And by raw documents, I mean job info, so like who owns the job, where it's running, what resources it requires. And then both of these, Graph and Elasticsearch, feed into our Grafana primary front end. And then we do also use Kibana, primarily for like service providers, and we need to do deep dive analytics into some of the data. So I got some quick stats on here. Our Graphite system's pretty modest, really. 1 node with a live replicated backup. We get about 500,000 data points per hour, 500,000 total metrics, and we're receiving about 1.5 million metrics per hour. Our Elasticsearch cluster, 6 nodes running on a cloud service, actually at the University of Nebraska, because we share it with some open science grid projects. All told, there's a bit over 1 billion documents and several terabytes of storage. And then our Grafana, we have several Grafanas, of course, several development and test Grafanas, and then several production for different organizations. But the main one, the Fifemon one, has about 400 registered users, 50 primary dashboards, and many more ones that I've got in test or dev, just a lot of ad hoc queries and such. And we see about 1 dashboard load a minute. I thought I'd show off some of the dashboards we have. So this is a high-level dashboards, just to kind of get a look over what the 5 experiments have been doing. This typically will show up in like a weekly status meeting for the lab or lab computing. So yeah, it just shows for each experiment how many jobs they've been running over time, total jobs run, and where those jobs were run. We also have an index and Elasticsearch of events, various outages, service degradations, and stuff. So we use Grafana's awesome annotations feature to put them right up there on the graph. And mainly that saves me from getting pinged on Slack or something. Hey, what happened here? I just put it right there. And then, so we also have something of a similar view for each experiment. Shows what each experiment's doing, and this is a scripted dashboard. But then we also show how well they've been doing their computation. So the 2 gauges on there. One shows what percentage of the jobs have been executing successfully, make sure that they didn't mess up and other jobs are failing and wasting resources. The other thing is to make sure that they're efficiently using the resources. So a job may be running, but really it's sitting there waiting for I/O or something. Like, a grad student may have run a little job on his Interactively, said, hey, this works great, and went ahead and submitted 10,000 of them, which are all hitting the MySQL database sitting on the computer in his office there, and that kind of grinds things to a halt. So we can get into more details on, for each experiment, what is currently happening in the batch system. You can see who's running jobs, where they're running. You can see what jobs are idle. You can see how long they've been idle. As you can see, there's also a summary table at the top. This is just an HTML panel with some JavaScript to build up a custom table. And you can drill down on that by clicking on a user's name and go to a even more detailed page for each user. So this user, what jobs they have running, where they're running, et cetera. And then you can also get for each cluster what the status of that cluster is. You see how many of those jobs are running, how many have problems that need to be looked at. We'll highlight those in red. And one of the things we're really focusing on is the resource utilization. That is, each job will say, I need to use this much RAM or this many CPUs. And we want to make sure that, of course, that they can't exceed it. Otherwise, we'll run out of RAM on a machine, possibly. And we also make sure they're not overestimating, because then we'll just be wasting resources that could otherwise be used by someone else. And then you can click on the cluster ID to drill down and see the status on individual jobs, and so on. But then for like cluster admins like me, we also want to see just collectively what the entire cluster is doing. So this is a look at one of our local clusters. So you can see how much is allocated and claimed by each job. That's the lighter color. And the darker color says how much they're actually using. So you can see like the green is memory, and jobs are typically claiming almost double what they have, or at least collectively they're claiming double. And this is a known problem that we started looking into. One issue is that many of our workflows will actually have spikes in memory, like in the middle of the job. They'll be processing these events, and some events may take more memory. So we're working with ways to improve that and increase the optimization of our system. And the other thing this is a more recent thing I've been pushing on, is one of the things I love about Grafana is how I can put together graphs from different data sources, text panels, et cetera. So instead of just looking at a graph and saying, oh, I think I see there's a problem there, you can also say, or if once you've identified there's a problem, where is the problem, or why is that? So instead of a checklist, go check these pages, you can just right there have a dashboard that walks you through it and gives you a graph to show you, help you answer if that's the problem. And then there's links right there to the individual service dashboard. So once you've said, oh, this is the service is the problem, now we can go look at and help figure out why that's the problem. And of course, as with any good monitoring system, we have lots of self-monitoring. We monitor the probes, their status, make sure that they're running smoothly, not getting hung up anywhere. Monitor our graphite system, make sure it's not having problems. And then, of course, Grafana's great built-in metrics in the dashboard off grafana.net. If you haven't turned that on, I highly recommend it. Although I have to admit, I'm still kind of fuzzy on what some of these mean. So maybe I need to pick somebody's ear on that. So this all started with just in the Fife system. But as these dashboards started showing in presentations and meetings, other groups and other organizations at the lab said, wow, that's really cool. Can we get monitoring like that? And so we expanded into what we call the landscape program, which is to take the same monitoring system that we use for Fife and incorporate these other systems. So we've started bringing in other CMS systems, so like the CMS high throughput computing system we started monitoring, and we're also started monitoring some of the HPC systems recently. So just a couple examples of that. This is a really recent example from supercomputing this year, where our HEP Cloud project, which is it's kind of an exploratory project into elastically expanding scientific computing from the traditional on-premises resources at our site and others into the commercial cloud. So I mean, if you look at a graph of our jobs, even the one I showed over a week, or if you look at that over a long time period, you see we're not running steadily. There's lots of spikes and peaks. So instead of investing in computers to meet maybe not quite the peak, but like the 2/3 peak or whatever that they do, maybe we can go a little bit lower for what our on-premises, and then use the commercial clouds when we need to do more. And so last year we did this with AWS. They gave us a grant to use their service to demonstrate this. And then this year Google came and gave us a grant and said, hey, we want you to do the same thing with ours, but we want you to do it bigger and better. And they wanted it done live. So we did this live at supercomputing every day. Using just the Google Compute Engine public API, or Google Cloud Platform, I guess. Start up, machines that can integrate it into our batch systems, started up jobs. And the goal was to be able to meet the current global capacity of the CMS experiment, which is, it varies, of course, depending upon how much they're actually running at the time. At this time, they were running about 150,000 jobs at a time. These are all single core jobs, I think. So we'll say 150,000 cores. And it was a huge success. They managed to do it. And it was a really big hit. I got a lot of compliments from Googlers, from other people. I wasn't actually at the conference, but I understand a lot of people at the conference love seeing Grafana up there. And you can see Google went ahead and tweeted out a screenshot of it, so I thought that was really cool. And then the other thing is the open science grid that I talked about. We're in the process of developing a new accounting system. That is to say, who's run jobs where, so that like a cluster owner can go in and see who's actually using their resources. And so it's a service Open Science Grid provides as part of it. So we had an aging system based on MySQL and with a Java front end and some, of course, homegrown graphs. And so we were hitting a lot of limitations with that. So now we've gone to a completely Elasticsearch based, and based on our experience with Grafana, we chose that to be used at the front end. And I'll send you a link to that a little later. That's open, and it's kind of in development, maybe alpha stage, so it's not great, perfect, but it's getting there. So as you can see, we really do love Grafana. Some of the things we really love is how easy it makes to view the status of systems and services. Things that previously would have required an expert to dig into. You may have to look at different sites, if any monitoring was actually even available, or you just have to start digging into logs. It makes it super easy, pulled together, and so almost anybody can look at the system status and see what's going on. And honestly, it makes me look good because of how easy it is to make dashboards. We might be sitting there in a meeting and someone will say, hey, I wonder what production processing did last week. And I can say, before you even move on to the next topic, I'll say, oh, I got a dashboard here, you can go check it out. Love the authentication that's built into it. We started off with LDAP. So while we are all about open science, due to mainly privacy concerns, we do have to put everything behind login. And recently, we've made a push to move everything into single sign-on, and that was just such a really breezy. Was really fast. I loved it. And of course, it's beautiful. Constantly getting compliments on how great everything looks. Wow, Fifemon's really cool. And I mean, I'll accept the compliment, but really they're complimenting Grafana and the great work you guys have been doing on the UI. And I love how easy it is to add extra features into it. So I've added custom plugins, which I may have forgotten to mention, but custom table plugins, and yeah, it's really easy. So we started off, like I said, with HTML and JavaScript, and it was almost easier to just write a plugin that did that and have the native look and feel, reloaded data when you refresh the dashboard. It's great. And we're also really loving the alerting feature, which I don't want to steal Torkel's thunder. I'm sure he's going to talk about that coming up. But I've been playing with that a ton. And I've just gone crazy building alerts and spamming our Slack channels with these. So yeah, our sysadmins have an established Ganglia and CheckMK system they've been used. So we're started working on some sensors into that to do alerting. But really, it's a pain. And yeah, I love being able to just do it right there on the dashboards, and the integration with Slack or emails. Wonderful. Of course, nothing is perfect. There are some things we'd like to see better. So one of the things I really love to be able to do, I'll have people come to me and say, hey, can I get a dashboard that shows X, Y, and Z graphs from these different dashboards? And say, yeah, okay, sure, I can probably do that. But there's really no good way for me to let them make their own. We tried playing around with organizations, but there were some issues with that. And one of the big things is just the broken URLs. And I know this has been beaten in the forums and such. But another thing is, I'd like to see some better ways to manage dashboards. So we treat dashboards as code. We have a development system where you make the dashboards, and you test them in pre-prod, and then you push them into production. So right now I have a little tool that I wrote to pull down the dashboards, put it into JSON files, and I can check them into Git, etc. But it all seems a little bit kludgy. I mean, maybe that is the way to go. Maybe we just need to make some better tools to do that. I'd like to see better Elasticsearch and non-time series support. I mean, it's definitely been improving, so I mean, yeah, just keep going with that. That's great. More drill down links. I love drill down links, and I think they're just a really intuitive way to navigate through the dashboard. So you can, click on an experiment's name, you can take you to the experiment's dashboard, click on user's name. So I think it'd be really cool if we could do that, like in a graph, you have a user's name there in the legend, click on that and go to their page. Of course, we also really like the interactivity features of being able to show and hide that. So definitely a UI challenge, but I think Raintank's got some pretty talented UX designers, so it's something to do. The other thing would be the ability to star dashboards with the saved template variable. So all of our dashboards, or almost all our dashboards, are templated to show different experiments and users. So I'd love to be a user to be able to just save their personal homepage or their batch details page as their homepage. So there we go. Here's some links. So we have a GitHub project. I have some of our dashboards and some of the probes we use to collect data on there. Honestly, I'm not so great at keeping it up, but check it out. Except the custom panels that we've built are on there. Landscape.fnl.gov, that's the project's kind of public website. It's actually running Grafana. We have a couple dashboards up there, but most of our dashboards are internal. You can check that out. And Grok is the open science grid accounting project we're working on. So like I said, it's kind of in alpha status, but you can check that out, how we're doing there. Of course, if you have any questions, feel free to stop me in a break or shoot me an email, or you can hit me up on Twitter. I don't use that much, but hey. Oh, okay. So we have some time for questions. Yeah, finally, I want to thank Torkel and the Raintank guys for such a great product, and the community, just a great community I've seen so far. So thank you guys, and take questions.
Hi, great talk. So you started to allude there at the end towards some of the stuff you're doing in terms of committing the change dashboards as code.
Yeah.
I'm kind of curious if you can elaborate, because it sounds like you probably do a lot of chat ops stuff there. Can you elaborate that? Have you had to do any customization to make Grafana more chat opsable, or is that something that you're trying to do or want to see?
I mean, just using a little tool, to use the API to just pull the dashboards down and commit them manually. Really, right now, it's no really good system that we put in place to do that. And then I'll just kind of manually, when it comes time to deploy to production, I'll manually push them out there.
Yeah, it was great. On the job scheduler, are you tying those job IDs that they can click on and then see all the time series information during that time the job was running? And if so, how did you couple those things together?
Yeah, that's something we actually have actively in development. So right now we're all focused on bulk statistics in the batch system. Something we're working on development is live profiling of these jobs. And like I had mentioned, some jobs will see spikes in memory and such. So we want to get a better idea what's happening with that. So we're working on hooking up a wrapper around the jobs that does live resource monitoring. And then using Beats by Elastic to send that back to a Kafka cache, and then use Logstash to put that into Elasticsearch right now. That's all really early in development, but I think.
Yeah. How do you correlate jobs with like users? Is it stored in your Graphite, or do you use like Elasticsearch?
Okay, yeah, in Graphite, we have a pretty detailed tree. So yeah, when our probes, when they collect the statistics on the jobs, they'll count up like the number of jobs running per user, per experiment, and even like if the jobs are running, it'll correlate by site. So we build this deep tree, and then we have various sub-aggregations under there so we don't have to put all the load on the front end to sum it all up. And then Elasticsearch, yeah, it just stores the data for each job as far as whose job it is and where it's running. Okay. Well, thank you guys. Enjoy the rest of the conference.